All right, section 2.4 is our last derivative rule that we're going to do. The last one. It's called the chain rule. And the chain rule has to do with functions that are sort of nested inside of another function. And in an algebra class somewhere along the way, whether it was pre-calculus in high school or an algebra 2 in high school, maybe it was college algebra here at OBU or somewhere else, we call these composite functions when we have functions nested inside of one another. So what you see in the chain rule is this left-hand side, before you take the derivative, is that composite function notation. G is inside of F, and then we have the derivative outside of all of it. So go ahead and write the rule down, and then we'll talk about what it looks like to actually do it. Everybody have it? I think we're done. Okay. Whoops, I'm going to switch too fast. Okay, so here's a function that if we were so inclined, we could multiply it out. I'm not so inclined. That's power of 5. I do not want to multiply 6 minus x squared times 6 minus x squared out 5 times. That does not appeal to me in the slightest. Okay? So while it is possible to do this particular one with algebra first and then do the derivative, it's not nice to do it with algebra first and then the derivative. So the chain rule is a much simpler way to process this problem. So what we want to notice is that there's something inside of something else. So the inside is a quadratic, right? And the outside part is the power of 5. So let's take a look back at the definition of how to do this. What this says is I take the derivative of whatever's on the outside. This time that we're looking at, it's a power of 5. Sometimes it's another function, like a square root function, or it may be a sine function as an outside function. There's lots of things it could be, okay? And I leave the inside untouched. The inside doesn't change when I take the derivative of the outside, okay? And then I multiply it by the derivative of the inside. So again, if you were thinking like, well, what would I expect it to be? You might expect the outside derivative and the inside derivative inside of it, and it's simply not the way that it works out. Kind of like we ran into those same issues with product rule and quotient rule back in 2.3, right? It wasn't quite what we expected it to be. It was a little more complicated than that. So when we're looking at this function, what I usually do, especially as I'm starting out and thinking as you guys start out, is that I want you to sort of think about that blue piece inside as just this blue blob. Okay, the blue blob, you can even draw it in, I'll draw mine in really dark so you almost can't see the words that are there. It's a blue blob. It has nothing to do with what I'm doing first. I'm dealing with a power of 5, and what do I do when I have a power of 5? And I'm taking a derivative. You move it to the front, right? You bring it down, you move it to the front, and you multiply it by what's there. So the 5, that's the exponent, gets multiplied by the 2 at the front to give you a 10. Okay? And then what happens to the power of 5? It becomes a power of 4. And what this definition says is that all I need to do is to rewrite the blue blob in the place of where the blue blob is. Well, I probably need to know what the blue blob is now, so let me erase it. It's 6 minus x squared. So I erase it, and I write 6 minus x squared. You can also just cover it up with your hand. Remind yourself, I don't want to touch this while I'm working with the outside function. After that, we'll color it in a little bit lighter. We need the derivative of the piece that was in blue. So we multiply that, and we want to take the derivative of 6 minus x squared. So what is the derivative of 6 minus x squared? Negative 2x is correct. I don't know about you, but that's far preferable to the multiplying out 6 minus x squared 5 times. Agreed? Not only that, but it's much more conducive to what we're going to be doing with these functions when we get to chapter 3. Having them in factored form is far more helpful than having them in completely expanded form. And at this point, I don't want you multiplying this out either. That's not hardly any better. It's a power of 4. I don't want to multiply out a power of 4 either, right? And it's again, it's not helpful to have it multiplied out. However, we should simplify a little bit of something. What makes sense to simplify here? Any thoughts?
The -2 and the 10.
Yeah, the 10 at the beginning, and then the -2x at the end. Those can combine really easily and cleanly. And again, it will be helpful for us if we do so later on for what I know is coming, right? So this is -20x at the beginning. And then we have the 6 minus x squared to the power 4 that follows. So this is f prime of x that we're finding and that we found. Is that okay? Okay, so it's the same process every time. The difference is that they all look a little different, right? This one was a power function. The next one doesn't even look like it is a chain rule. It doesn't really look like there's something inside of something else, and so you have to sort of think about how could it be written in that way. Now, could you use the quotient rule on this? Yes, you could. Absolutely could use the quotient rule, and it would be completely correct. But there's another way to do it too. So for what we're going to look at today, I want to show you how to think of it from the chain rule perspective, and then when you see it later, you have a choice. If you think of it as a quotient rule and you do it that way, fabulous. If you think of it as a chain rule and do it that way, fabulous. And what happens is that on the gateway, when I have multiple options, I just have answer keys for both of those options because they look different when they're not simplified, right? If they're not simplified and you used the chain rule, it's not going to look like the non-simplified one using the quotient rule. So I just have two versions on my answer key and either one's good. Okay? All right. So how can I make this look like a chain rule? Well, do you remember in the last section we had, it was our very first example for today, and it had an x in the denominator, and I said we can pull the x up and make it negative. We can do that here too, but we have to be a little more careful. We have not just x in the denominator, we have a whole string of stuff in the denominator. So we take the entire denominator and we move the entire denominator up and we put a -1 on it. Okay, it's all got to stick together. You can't just make the x squared x to the -2 and the 3x x to the -1, and then you're left wondering, what do I do with -1? Right? You can't do that. That doesn't work. But what you can do is you can move it all up. So we can go x squared plus 3x minus 1 and make that a power -1. And interestingly enough, at this point, it really looks a lot like what we did over here, doesn't it? You got a power rule problem inside of that chain rule. Okay, so I'm not going to cover it up completely because I can't erase it very well, or I'll just erase everything. Okay, so this is the blue part. The outside derivative is going to be the dealing with the power of -1, right? So what are we going to do with the -1? Yeah, we're going to move it to the front. So g prime of x has us move the negative to the front. And what will the new exponent be? -2. And the chain rule says that the blue piece, which is my inside function, will simply be rewritten. So it's x squared plus 3x minus 1. Simply be rewritten. After that, what do? The derivative of the blue part, the part that's inside. So I need the derivative of x squared plus 3x minus 1. What is that? 2x plus 3. On the gateway, you stop here. And you can see that looks nothing like what you might have expected it to look like if you did a quotient rule, right? It doesn't. This is the gateway stop spot. However, if we simplify it and clean it up, you're going to start to see why it will look or mimic what we would have gotten with a quotient rule. So let's take a look at that. So if I take a look at simplifying and cleaning this up, the part that's to the -2, this piece, is going to dump back down into the denominator. Okay? So in the denominator, it will still have to be in parentheses, but I have x squared plus 3x minus 1 squared. Well, isn't that the denominator squared? Most certainly is. That's what the quotient rule would have given me. The other pieces don't go into the denominator. Namely, the negative at the beginning is just going to be either out in front if you wish, or moved up. I'm going to move mine up. And the 2x plus 3, was it plus 3 or minus 3? Plus 3. The 2x plus 3 at the end, it stays in the numerator as well. So I'm going to take this negative and this 2x plus 3, and I'm going to move the negative through it so that I get negative 2x minus 3 in my numerator. Now, we mentioned last time that if we have the ability to factor something and simplify, we will. This denominator won't factor. I can't factor x squared plus 3x minus 1 in the real numbers and get them to cancel out with the numerator part. That's not going to work, or at least not with rational numbers. And at the very least, it's certainly never going to look like negative 2x minus 3 or even 2x plus 3, right? Because it's x squared in the denominator and I have 2x in the numerator. Like, that's not going to be possible to simplify it. So even if it factored, it wouldn't factor into something helpful. So I don't want to factor things, even if I can, if it's not helpful at this point. So at this point, this one is completely finished. What do you think? I mentioned that the denominator seems reasonable. Why would the numerator be reasonable? Well, the numerator, part of it, if you used the quotient rule, what would you get if you took the derivative of this numerator? The derivative of the numerator of the original function. Up here, what's the derivative of this? It's 0. So if you think about the quotient rule, there's two pieces of the quotient rule with the subtraction sign in between, but one of them is going to be 0 because the derivative of the numerator is 0. Right? The other piece is going to be the numerator, which is a 1, times the derivative of the denominator. Well, the derivative of the denominator, that was the 2x plus 3. So you're seeing that piece show up again. So if you did a quotient rule and I did a chain rule and we both simplified it to this point, our answers would be identical. Yeah? It would. So that's an expectation, too, if you're looking at something and you're like, well, you did it that way and I did it this way. We got different answers, but maybe that's okay. Well, maybe it's not okay. Be careful. Look at the algebra that you simplified and double check things, as well as the calculus part. Okay, number 3 is the most challenging one we're going to do today, and it's our last one we're going to do today. Y'all ready? Okay. This is a messy one. Okay? I'm not going to make it sound pretty. It's not. It's ugly. It's terrible even. Tell me something you see. I see a quotient rule. Yeah. Do you see the chain rule? No, it's okay. Is there something inside of something else? There is. There's this quotient rule that's inside of a square root. You see it? Okay. That's how we're going to do the problem first. I'm going to show you another way to see it after we do that, because there is an alternate way to see it. But I think that's the most reasonable one to see, especially because you guys already saw the quotient rule part right away. Okay? So the first thing we're going to do is we're going to rewrite this as the quotient rule that it is, so 3t squared. And feel free, as far as I'm concerned, you can change t's to x's if you see them on like written work or quizzes or something like that. WebAssign's not going to let you, so be careful to keep whatever variable they use in WebAssign and use it throughout your problem, okay? I'll keep mine as t squared, or as t, but just make sure your t's look like t's and not pluses. The denominator, 2t plus 3. And do you remember what the square root is as an exponent? It's a 1/2, right? Okay? So this piece is my inside function, the quotient part is. All right, h prime of t. If this part's not bad, what do I do with a 1/2? Move it to front. So I have 1/2 in front. What will my exponent be? It will be negative 1/2. So 1/2 minus 1 is negative 1/2. Remind me if I forget on Wednesday, we're going to talk about the gateway in terms of exponents later. I don't want to confuse the issue right now, but we'll mention it on Wednesday. Why I keep saying Thursday. Okay. The blue part, the quotient part, needs to be rewritten where it was. So 3t squared minus 2 and 2t plus 3. It looks messy enough that maybe we would stop there, but it is not finished. All we did was the outside, right? We didn't do the quotient rule that you guys noticed on the get-go, right? We still need to do that quotient rule. All right, so the quotient rule gets multiplied here. All right, so how do I start the quotient rule? Low to high. So low is 2t plus 3. What's the d high part?
6t.
6t. And then minus, right? And then we need high d low. So high, the numerator, 3t squared minus 2. D low times 2, right? All over
2t plus 3 all squared.
2t plus 3 all squared. And on the gateway, you stop there and you breathe a sigh of relief because you're not going to like the simplification we're about to do. Okay? Is the derivative part okay, though? Yeah? All right. This is our derivative, but we don't get to leave it that way. So let's think about some of the things that we can do. So one of the things that we might want to take care of is noticing, do you see the denominators are still the same? This one says 2t plus 3 here, and this one says 2t plus 3 here, so we might have the chance of like somehow consolidating those. And we do have that chance. So we want to be able to kind of do that. You might also notice that this numerator on the quotient rule part is kind of a mess, and it probably will simplify at least something if we distribute things out. Maybe we can collapse some things. So we're going to attempt to do that too. So those are two things we're going to do. The 1/2 at the beginning, we're just going to leave it as 1/2 now. It will be able to help us reduce some stuff later, but even if it weren't, it's not helpful at the moment. So I'm just going to sort of ignore it and just rewrite it for the moment. So right now, we're going to rewrite this first piece as 3t squared minus 2, and we're going to put this as a power negative 1/2. And we're going to put the 2t plus 3 to the power of negative 1/2. So we're just moving the negative 1/2 to each the numerator and denominator separately. That's a property of exponents that you learned a long time ago. You're allowed to do that. And then at the same time, let's go ahead and clean up that numerator. So I have 2t plus 3 squared on bottom. So we'll distribute through the 6t. What will that give us?
6t squared.
Close, 12t squared.
Well, yeah.
And then what?
18t.
Right, plus 18t. That sounded like I said AT&T. It's not what I said. Okay, let me move that over. Cool. And then I'm going to distribute both the negative and the 2 through to the 3t squared into the negative 2. So what is the 3t squared times negative 2?
6t squared.
Yeah, and it's negative, right? Negative 6t squared, and then
Positive 4.
positive 4. Okay, so looking at that numerator, do you see some pieces that might be able to be reduced or simplified? A couple of them anyway, right?
T squared.
Yeah, these two right here can combine. Okay, so at the moment, I'm going to leave the first numerator where it is. It's not going to stay there forever, but for the moment it is. So 3t squared minus 2 to the negative 1/2. I am going to push these pieces in together. So this 12t squared minus 6t squared would be 6t squared. And then I have plus 18t plus 4. And then take a look at what happens. This is a power of negative 1/2, and this is a power of positive 2. Properties of exponents say I can combine them because they have the exact same parenthesis part, right? Their bases match. What would their exponent be? 1.5 or 3/2, right? So because 1.5 might look a little bit more like 11/2 because of the way we write it, I'm going to err on the side of improper fractions and write 3.5. If your 1.5 is abundantly clear, I'll let it go. But make sure it's abundantly clear if you choose to do that. So this is 2t plus 3 to the 3/2. Okay, it's looking better. Agree? It is looking better. There's two things we can do still. We can move this negative 1/2 to the denominator and make it a positive 1/2. So we'll do that. And then what that leaves on top is a 6, an 18, and a 4, which happen to be all even, and a 1/2 at the beginning where the 2 will reduce with it. So this 2 at the beginning will make this a 3, a 9, and a 2. So now I have, this is our last step, 3t squared plus 9t plus 2 over, and it doesn't matter the order I write these in, I'll just write the power of negative 1/2, the one that's moving down, as positive 1/2 first. So 3t squared minus 2 to the 1/2 times 2t plus 3 to the 3/2. And we all said, is it over? Right? This is hard. This is a hard problem. Okay, it really is. So this is, we're doing h, right? H prime of t. And we're finished. I'm not going to show you the full worked out other way to do it, but I do want to show you the other way you can recognize this. I'm not sure that it's any easier, it's just different. It's probably the same amount of work. We recognized that this was a quotient rule raised to a power of 1/2. So there's a quotient inside of a chain. That's what we recognized, right? So the other way that we can recognize it is that we could recognize this, and I'm going to shrink this down and move it over in case you're still writing a bit, is that you could recognize this instead as a chain rule inside of the quotient. So it could be written instead as 3t squared minus 2 to the 1/2 over 2t plus 3 to the 1/2. Or even if you prefer, you could move the denominator up to the numerator and do it as a product rule. That would be a third way to do that as well. I want to show you what the derivative looks like so that you can see what I mean when I'm saying like your derivative doesn't look the same. I'm just not going to show the algebra simplification for it, okay? So I'm going to show you one more thought on how to do a derivative for this. So we're dealing with h prime of t. Try that again. And if I'm dealing with this from the perspective of a chain inside of a quotient, like we have now, what happens is that I've got a quotient rule. Well, the quotient rule says low. I write the low part first. Well, the low part is 2t, whoops, let's go back to black. 2t plus 3 to the 1/2. That's the derivative of what's on denominator, or that's the original of what's in the denominator. And then I multiply it by the derivative of the numerator, but the derivative of the numerator has a chain rule in it, right? It's this piece to the power 1/2. So the chain rule says I bring the 1/2 down, I rewrite the inside, 3t squared minus 2, and I make it to the power 1 less, so negative 1/2. And I multiply by the derivative of the inside, which is 6t. Is everybody okay with me erasing what's on the left-hand side at this point so I can have a little more space to write? Does everybody have this part written down? Are you good, Dylan, on the left-hand side of this? Yeah, okay. And then I'll shift it over. Oh, I was close. Okay. And then I would have the subtraction, and I would have, so it was low d high, now we have high d low. So high, the part on top, that's the 3t squared minus 2 to the power of 1/2. And I want the derivative of what's on bottom. Well, the derivative of what's on bottom is going to mimic a lot like when I did the derivative of what's on top. I'm going to bring down a 1/2. I'm going to rewrite the 2t plus 3. And I'm going to make it to the power 1 less, which is negative 1/2. And then I'm going to do the derivative of the inside, which is 2. Now what's interesting is that the derivative, or sorry, not the derivative, but the denominator squared is actually very friendly. While that numerator is pretty atrocious, the denominator squared is friendly. What happens when I take 2t plus 3 to the 1/2 and then I square it? Yeah, the squared cancels out with the 1/2. So again, I'll write it so you can see it, but this is 2t plus 3 to the 1/2, and then it's squared. So these pieces cancel, so my denominator is really just 2t plus 3. And I'll tell you what, that doesn't look anything like the first step we did in the other direction, does it? Not in the slightest. It's perfectly the same thing. If we do all the simplification, it'll be perfectly the same thing. I think the simplification might be a little bit harder to see some of the pieces move around, but it is still a viable option. Okay? Any questions before we finish up today? Okay, we will pick up with example 4 next time. What I would like for you to do as well, and I'll send you an announcement reminder inside of Canvas, is we're going to take a look at the last part of this lesson, and we're going to work on the derivative review. I'd like for you guys to print that out. It is posted inside of Canvas. I'll bring a couple of extra, but if like none of you bring it, then you're going to be like taking pictures of it and have to work from your phone. It's going to be annoying, okay? There's a printout inside of Canvas. There's also a solution set for that printout. So if you want to print out the solution set as well, you're welcome to, so that you can check as you go. Yes, sir.
When are we going to get